When working with binomial distributions, we'll often need to use the complement, and in particular the complement formula that we'll learn in this video. Now, the idea is we'll frequently need to find the probability of there being at least r successes in some experiment, where r is some positive integer. For instance, let's say we're given the probability of it raining on any one day in November. We may be asked to find the probability of it raining for at least 10 days next November. Now, some key terms to pick up on here are the terms at least and also more than. Now, the complement formula is the following. The probability of x being greater than r is equal to 1 minus the probability of x being less than or equal to r. Now let's try and explain what we mean here. Let's say we're given a discrete random variable, capital X, which follows a binomial distribution. And say for argument's sake that there are 6 trials, so n is equal to 6. Let's say we're interested in finding the probability of there being at least 2 successes. In other words, we want capital X to be greater than or equal to 2. And the first thing to realize here is, well, x can be equal to either of the following: 0, 1, 2, 3, 4, 5, or 6. Because remember, there are 6 trials in this experiment. And there can be either 1, 2, 3, 4, 5, or 6 successes in this experiment. Now, x being greater than or equal to 2 is exactly the same thing as saying that x is greater than 1. So what we're looking for here is the probability of x being greater than 1. And now, using the complement formula, this is equal to 1 minus the probability of x being less than or equal to 1. And there we have it. That's what the complement formula tells us. So let's go ahead and see how we can use this with an example. We're told that a biased coin is such that the probability of flipping tails is 0.3. The coin is flipped 5 times, and we're asked to find the probability of obtaining at least 3 tails. Now, first thing to pick up on here, of course, is the fact that we can see we've got our key term at least, which I'm boxing now. Now, this biased coin, of course, follows a binomial distribution. Each flip is independent of the previous, and we can see that we have 5 trials, so n is equal to 5. The probability of a success is 0.3, so p is equal to 0.3, and of course, we define the discrete random variable capital X here as being the number of tails obtained, or number of times we flipped tails. Okay, now because the probability of a success is 0.3, the probability of a failure, which we call Q, is equal to 1 minus 0.3, which is equal to 0.7. And there we go. So we're interested in finding the probability of obtaining at least 3 tails. So that's the same thing as probability of x greater than or equal to 3. But this is also the same thing as probability of x being greater than 2. And now we can use our complement formula. Remember, that was probability of x being greater than r equals to 1 minus the probability of x being less than or equal to r. So let's go ahead and write that. That leads us to 1 minus the probability of x being less than or equal to 2. And now we know from our cumulative distribution formula that this is equal to 1 minus the probability of x being equal to 0 plus the probability of x being equal to 1 plus the probability of x being equal to 2. And now for each of these probabilities, we need to use our classic binomial distribution formula, which I've just shown here in green. So we can go right ahead here and say that's equal to 1 minus binomial coefficient 5, 0 times p to the power of 0 times q to the power of 5 plus 5, 1 p to the power of 1 times q to the power of 4 plus 5/2 times p to the power of 2 times q to the power of 3. And we close those parentheses. Now replacing all of these by their respective values, that leads us to 1 minus 1 times 0.7 to the power of 5 plus 5 times 0.3 times 0.7 to the power of 4 plus 10 times 0.3 squared times 0.7 cubed. And now using a calculator, we find that this is equal to 1 minus 0.83692, which leads us to 0.16308. And now, of course, rounding to 3 significant figures, we find the probability of x being greater than or equal to 3 is equal to 0.163. And there we go. That is the probability of obtaining at least 3 tails with this biased coin. And so this is how we would use the complement formula. And there we go. Hope it helps.